Okay, so this video I'm going to take a look at resolving vectors into perpendicular components and also look at combining vectors to calculate magnitude and direction of the resultant. So let's start off with resolving vectors. So in this diagram here we've got a certain vector, and this is going to be a velocity vector in this case, but it doesn't particularly matter, and it's going this direction. And in this example I'm going to define the I and j directions as these ones here, so horizontal is I and j is vertical. And I'll show you on the next slide an example where I don't do that and it makes it easier. So anyway, those are two directions, so we need to work out the components of v in each of those directions. So v is at an angle theta to the horizontal I direction. That means that the component of v in the I direction is v cosine theta, and it also means that the component in the vertical direction is v sine theta, since this angle up here would be 90 minus theta. Okay, so that's how you can construct it, and you can see here that what you should end up with is two vectors that are tip to tail, so this one's tip is at the other one's tail, and these two combine together to give you v. So why do we use I, j and k and not x, y and z like you would usually used when you're doing graphs? The key thing is we can change the direction of I, j and k, so they don't have to be horizontal, vertical and into the page, and that's quite useful, as you'll see in the next slide when we're dealing with things that are at an angle. So in terms of expressing the motion of this one v, we can do it in two ways. We can do it as a column vector or as an ijk notation. In terms of ijk notation, you would have to define which way your I and j were, and then you can see here we've got the component in the I direction multiplied by I plus the component in the j direction multiplied by j, and you've got the component in the k direction, which in this case is 0, multiplied by k. If it's 0, you don't have to write it, you can forget about it, but I just thought I'd throw it in there so you could see what the general format looks like. And here, in terms of a column vector that describes its motion, again we've got the I direction, we've got the j component, and we've got the k, and it's perfectly permissible to, if there's nothing to do with k in the question, not include the k, and then you can just give a two-piece column vector. But again, I just want to show you what it looks like. So this is your I, this is your j, and this is your k down here. So let's have a look at an example. Okay, so this is why it's useful to use I, j and k and not x, y, z, because we can change the direction of them. So because we're dealing with a slope, we're going to change it so I is the positive I direction is down the slope, and the positive j direction is up, out of the slope. We can see here our slope is angled at 30 degrees. So let's draw some forces on here. So we've got the weight force, mg, acting down, and then we need to think about resolving that into parallel components. So we've got this part here, and we've got this part in here. So we need to take a look and work out what these two angles are. So in here, this will be 30 degrees, and in this, it will be 60 degrees. So in the direction down the slope, we're only interested in the I direction here, so we can forget about the j direction. So I think in terms of calculations, acceleration is force divided by mass. That's just Newton's second law there. And then the force is mg. We want the component in the I direction, so down the slope, so times cosine of 60, and then we're going to divide by m, so actually the mass is completely inconsequential here, and just gives you g cosine 60. So that's the acceleration down the slope or in the I direction. If we wanted to know what the reactionary force of the block was, that would just be the other component, but that's not what I was asked for, so I'm not going to talk about that now. Okay, so that's resolving vectors into perpendicular components. Let's have a look at combining together vectors. So if you have two vectors acting, say, on an object, two types of velocity, two forces, whatever it is, and you want to find out what the resultant is, you need to combine them together. And the way to do that is to arrange them tip to tail. So you can see here, once again, we've got them tip to tail here. So it's been acted on by A and then acted on by B. And that's going to give your overall resultant, which I've called V. And what we want to know is what the magnitude of V is and what the direction theta is. And we're going to use two fairly simple rules to get to this. So we can use the cosine rule and we can use the sine rule here. So this is your cosine rule. This is the general expression of your cosine rule, where this is the resultant. So A is the resultant, and in this case B is A, and then C is B squared, so we're changing letters a bit. And we've got our 2AB cosine C, and C is this angle here in this case. So that's something we can use a bit later on. And then we've also got the sine rule, which is something like this. So sine C, in this case, this is sine C, and the side opposite C is V, so it's sine C over V. And we've got theta, and the side opposite theta is B, so it will be sine theta over B. And again, this relationship will prove useful in a second. So let's look at a worked example with these in. So our boat's travelling at 3 meters per second, so let's draw that in. So we've got 3, and it's acted on by, and it drives into a river flowing at 1 meters per second at 60 degrees. So we want to arrange these tip to tail. And we know that there is 60 degrees, so then you know it's at an angle of 60 degrees. So what we want to find is the resultant V, and we also want to know what this angle is in here, theta. And we know, so let's just add in, that is travelling at 1 there. So first of all, some key information. So let's do some deduction. So this angle in here must be 180 minus 60, which is equal to 120 degrees, because those two angles together make like a straight line, if you like. So we've got all we need to employ the cosine rule. So we've got V squared is going to be 3 squared plus 1 squared minus 2 times 3 times 1 times by the cosine of 120. And which means you can calculate V by square rooting that whole expression there. So 3 squared plus 1 squared gives you 9 plus gives you 10 minus 6 cosine of 120, which gives you 3.61 meters per second. To 3 significant figures. And then if we want to calculate the angle theta, we're going to have to employ the cosine rule, sine rule in this case. So we've got, what round do we want this? So the general expression of this would be, so in this case, sine theta, and the side opposite theta is 1. That's equal to sine B, so that's going to be sine 120 divided by V, which gives you theta equal to 13.9 degrees again to 3 sig figs. Okay, so that's just some quick worked examples to show you combining and resolving. I suggest you have a go at the questions which I've linked in the description underneath the video, which gives you a chance to test out whether you've really understood this material. I'll be following this video up shortly with my next video in the Mechanics 1 series.